Hello dear friends, how are you all? Welcome to my YouTube channel. So in this session we are going to discuss about one of the most important concepts in electrostatics, that is electric flux, wherein we will be learning about what is the formula for electric flux, what is Gauss Law in electrostatics, and on which we have different applications also, like three different applications are there: electric field due to linear charge density, electric field due to surface charge density. In that, two types are there. One is plane sheet and the other one is sphere. So we'll learn about them one by one. First, what is electric flux and what are the, where can we apply them, which are very important for your competitive examinations. So in this video we'll try to cover up the basic concepts. Shall we start? So the electric flux, here if I consider an area, okay, let me consider here there is some area like this. So we define a term called area vector, okay, area vector. So actually area is a scalar quantity, but here we consider area as the vector. So area vector is perpendicular to what is that? Area. For example, here the area is A, then its area vector is represented by this A. So area vector, for example, here if this is the area vector is represented perpendicular to it. If this is the area, perpendicular to it. If this is the area, perpendicular. Area vector is represented perpendicular to it. Now let us consider there are electric field lines entering this area and moving in this direction, entering this area, moving in this direction. Okay, so this is the electric field line. This is the electric field lines which are passing through this area. Now how to define electric flux? Electric flux is defined as electric flux is defined as number of field lines, number of electric field lines passing normal to the given area. Okay, sir, here electric field lines are not passing normal to the given area. Normal is perpendicular to the given area. They are making some angle here. Okay, so here if you consider there is some angle between area vector and electric field vector. Now how to define electric field, electric flux? Electric flux is defined as component of electric field along x-axis will be E cos theta into area will give you electric flux. So electric flux is equal to EA cos theta. Okay, or this can also be written as E dot A, because electric flux is a scalar quantity. It is a scalar quantity. Number of field lines passing normal to the given area will give you electric flux, and this is the formula for it. Sir, what is the SI unit, sir? So its SI unit is given by Weber, or you can write it as WB. Next, in terms of electric field and area, if you want to write, you can write electric field, it is Newton per coulomb, area meter square. So Newton meter square per coulomb you can write, or electric field unit is volt per meter into meter square is voltmeter. Like this, different units you can write for voltmeter for electric flux. So these are the different units. Okay. Now, sir, what is the dimensional formula for electric flux? We can just derive it. Let me derive here. Dimensions. okay, dimensions. So electric flux is given by E into A. Can we write E is equal to F by Q that we have derived in the beginning, okay, into area is there. Can we write F is equal to ma, Newton's second law, divided by charge can be written as I into T, current into time, area is A. So let me write the units for kg, mass it is kg, acceleration meter per second square, and area meter square, divided by, for current it is ampere, time it is second. So from this you will get kg meter square per second square, correct? No, kg meter square into m is meter cube, second divided by second, so second cube, then we have ampere minus 1. So therefore dimensions are given by, for kg m power 1, meter L power 3, second T power minus 3, ampere A power minus 1. This is the dimensional formula for electric flux. Okay, sir, how to write the differential form of electric flux? The differential form of electric flux is given by small d phi is equal to E dot dA. Sir, where do we use it, sir? I will tell you, I will give an example. And if you want the integral form here, just integrate on both sides, we will get electric flux is equal to E dot dA, area integral. So this is for the extended surface, extended surface means surface is not closed. If you have a closed surface, electric flux is given by integration with this symbol, okay. This is for closed surface, E dot dA for closed surface, phi is equal to E dot dA. So this is about the basics of electric flux in terms of E and A, okay. Now let us take one more situation. Sir, when do we get maximum electric flux and when do we get minimum electric flux? We'll discuss about it now, okay. For maximum electric flux, phi is equal to E into A into cos theta. For flux to be maximum, so what should be the value of tan cos theta? Cos theta should be 1, E into A, for which since cos theta is equal to 1, for what value of theta will get 1, so theta should be 0. That means the angle between electric field and area vector is, electric field should be parallel to area vector, not area, it is area vector. That means if I consider some area here, okay, I will consider some area here, and area vector is given in this direction, okay. If electric field is parallel to it, electric field is parallel to the area vector, then theta will be 0. So cos 0 is equal to 1. Then we will get maximum electric flux. If electric field is perpendicular to area but parallel to area vector, perpendicular to area or parallel to area vector, then the flux will be maximum. So when do we get minimum electric flux? So flux will be minimum when what is this, phi is equal to 0, or this you will get when cos theta is equal to 0 or theta is equal to 90 degree. That means electric field vector is perpendicular to area vector or parallel to area. So this is the area, okay. So area vector is in this direction, but electric field is passing parallel to the area, electric field is passing in this direction. Now the angle between these two is 90 degree. Theta is equal to 90 degree. Now what is cos 90? 0. So flux is 0 because E into A into cos 0 is 0. Minimum flux. So maximum flux, minimum flux. Do understand this. This is very, very important one. Next we have one more case. Sir, I have a charge here and there is some random surface like this, closed surface like this. I need to find out the flux through this surface, closed surface. So what is the flux through this closed surface? So the flux is like this. Electric field is outwards, means it is a positive charge. Now if you observe, here the area vector is in this direction, dA, but electric field is in this direction. What is the angle? Theta. Here area vector, if you consider, it is in this direction, theta, making an angle A. Here area vector is perpendicular to area, making an angle theta. Theta, different thetas I am talking about. So here area vector is in the direction of electric field, so angle is 0. Here some angle is there, here also there is some angle, here also in this direction, here in this direction, here in this direction. So everywhere if you observe, the direction of electric flux is different. So what I have to do is, I need to find out the electric flux at each and every point, then we have to add. So the total electric flux is given by flux at each and every small areas. Won't it become very difficult? Okay. So then flux will be given by integral d phi, that is equal to closed integral E dot dA. This we have just studied in the what is that electric flux formula, that is in integral form, right? So we may have to use this formula and find the total flux. To make our work easier, this integration part and all, we have a law called Gauss Law in electrostatics. Let us learn about it now. Gauss Law in electrostatics. Very, very important one. GEUSS, apostrophe P.S. Gauss Law in electrostatics. Gauss Law in electrostatics. Is it clear? Now, so what is the statement of Gauss Law? Let me write the statement first. It states that Gauss Law in electrostatics states that total electric flux through the closed surface, through a closed surface, okay, closed surface is equal to 1 divided by epsilon naught times charge enclosed, 1 by epsilon times charge enclosed. That is Gauss Law in electrostatics. Mathematically, it is given by phi is equal to 1 by epsilon naught times the charge enclosed. Sir, what does it mean, sir? Let me give an example. So, let us consider there is a closed surface here in which we have charge q1, q2, q3, q4, q5. So, let us consider q2 and q3 are negative and q6, q7 are there. Enclosed charges means this charge, enclosed charge is q1, q2, q3, q4 and q5. Therefore, q enclosed is given by q1 minus q2 minus q3 plus q4 and q5. You should not consider outside one for enclosed charges. Okay. Now, if I compare it with the previous formula that we have written, that is electric flux is equal to, in terms of integration, closed loop, for the closed loop, E dot dA. So, there is electric flux outwards, which is equal to this one, Q enclosed charge divided by epsilon naught. Okay. This electric field is there, right? This electric field is due to all these charges, even including Q6 and Q7, not only Q1, Q2, Q3, Q4, Q5 and Q6, Q5, it is also with Q6 and Q7 due to all charges, outside as well as inside, outside and inside. But Q enclosed is only for enclosed charges. Look at the same formula, this depends on all the charges, this depends on only enclosed charges. Okay. So, where epsilon naught is absolute permeability, whose value is 8.854 into 10 to the power minus 12 farad per meter, or it can be given by Coulomb square per meter square per Newton. Coulomb square per meter square per Newton is the unit for epsilon, absolute permeability. Sorry, permittivity, absolute permittivity of free space. Okay. This is about the basics. Now, based on this, in competitive examinations, there are some special cases. Shall we discuss about it? Yes, just a minute. Yes. Okay, so here we have few special cases. Let us learn about them. So, this is the surface. Okay, imagine surface called Gaussian surface. Gaussian surface. Sir, what is Gaussian surface, sir? So, it is the imaginary surface to which we can apply Gauss Law. It is the imaginary surface to which we can apply Gauss Law. So, this is just the shape of the Gaussian surface. It can be of any shape. It need not be spherical. It can be cuboidal also, cubical also. It's up to you. Cylindrical surface. It's up to you which kind of shape that you need to consider, that you can consider. Okay. Now, if there is a charge in the closed Gaussian surface, what is the flux through this surface? Flux through the surface can be given by Q enclosed divided by, okay, or net charge inside the this one divided by epsilon naught, not net charge, let me consider enclosed only. So enclosed charges, one is positive charge, one is negative charge, right? What is dipole, electric dipole? Two equal and opposite charges separated by small distance. So q minus q is 0, the flux through the cube is 0. Okay, this is one thing. Now here we have a sphere on which charge is distributed uniformly. How much? Q amount of charge. What is the electric flux through this surface? Wherein the charge is distributed equally. This side q by 2 charges are there, this side q by 2 charges are there. Now write the flux. Flux is given by charge enclosed by this is q by 2 divided by epsilon naught. So that is a electric flux through this what is this? This sphere, Gaussian sphere, is phi is equal to q by 2 epsilon naught. This will be asked in competitive exams like KCET, NEET and JEE. Now here we have a closed surface, inside also charges are there, outside also charges are there. So flux is given by only inside charges, 2 minus 3 plus 4. Okay, 2 minus 3 plus 4 coulomb divided by epsilon naught. So how much is that? Outside we will not consider. So even if it is there 5 coulomb, 6 coulomb outside is there, don't consider. Phi is equal to, so minus 1, 3 coulomb divided by epsilon naught. If you want to substitute, you can substitute the value of epsilon naught and calculate. That is 8.854 into 10 to the power minus 12 units farad per meter. You can substitute and calculate this. Okay. Now here we have special case. This is very important, okay, for competitive exams, wherein we have a hemisphere, half of the sphere. On this surface there is a charge placed. What is the electric flux through it? Not in and out, let's consider this in different case. So what is the flux through this hemisphere? Flux through this hemisphere is given by, can you answer? Look at this, let me draw an example, diagram here. So some of the flux is going outside and equal amount of flux is going inside. If the charge is placed on its bottom surface at its center, half of the flux will go down and half of the flux will enter this. Therefore, the flux entering this hemisphere is given by q by 2 epsilon naught. We just have to divide the total flux by 2 so that half of the flux entering the hemisphere. So here also similar, some of the flux is coming out. Okay, the flux coming out and some flux is going inside. Okay, so total flux is equal to flux entering the cone is equal to q by 2 epsilon naught. Okay, like this we have few more examples. Let us discuss about them. Okay, so let's consider there is a cube here. Like this. Okay, so the charge is placed inside it. Charge is inside the cube. Now what is the electric flux through the cube? So since the charge is present inside the cube, flux is given by charge enclosed by epsilon naught. Charge enclosed by the sphere is q, what is this? Cube is q divided by epsilon naught. That's it. This is the flux through the cube. Q by epsilon naught. Now answer me, what is the flux through each face? I want the flux through any one of the faces. Let's consider what is the flux through this face, this shaded one. Each face is given by q divided by, so total flux through the cube is divided by 6 because it has 6 equally divided area. Okay, so that is called phase. 6 equal phases are there, so divided by 6 will give you flux through each phase is given by q by epsilon naught divided by 6. Very important one, if the charge is present inside the cube. So let us consider next one, where I will consider the charge on the face of the cube. Okay. Now if the charge is present on its face, okay, the charge is present on its face, on the face. Now tell me, what is the flux through the cube? What is the flux through the cube? Since the charge is placed on the surface, we don't have the Gaussian enclosed charge here. So what I will do is, I will consider one more cube this side, imaginary cube, okay, of equal length. Let me consider there is a cube here, imaginary surface. So half of the flux is entering this cube and half of the flux is entering this cube. Therefore, flux through the cube is equal to q by 2 epsilon naught. Equally it is divided. Yes or no? Half of the flux is entering this cube, half of the flux is entering this cube. So therefore flux is 0. Now what is it? Q by 2 epsilon naught. Now what is the flux through each phase? What is the flux through each phase? Now how many phases you have to consider? Only 5. Because if you consider the charge is placed on this phase, there will be if the charge is placed here, let me consider like this. Oh, this is the charge. So there will be electric flux passing parallel to this area, right? So this is the electric flux parallel. So the flux will be how much? 0. On which surface the charge is present? Okay, just a minute. On which surface the charge is present, that surface you should not consider. So one surface left, remaining 5 surfaces are there. So divide this one by 5, you will get for phase. Flux through each phase is equal to flux through the cube divided by 5. So phase is equal to cube is q by 2 epsilon, 2 5 is a 10. So q by 10 epsilon naught. Okay, now let me consider one more case. All these are very important for competitive exams. Let me draw some small diagrams. Here we have a cube. Here we have a cube. A charge is placed on the edge here. Okay, on this edge, charge is on the edge. So what happens now? The charge is distributed to how many cubes now? 4 cubes. Sir, how sir? Flux through the cube is equal to, so if I consider there is a cube kind of thing here, let's consider this is the cube. Okay, this is the cube. If I place a charge here, I can place one cube here, one cube here. Okay, 1 2 3 and this is 4. So 2 cube here top 2 cubes. Okay, total 4 cubes will be there. Therefore, what happens here, flux is divided into 4 parts, q by 4 epsilon naught. So when you consider each face, 2 surfaces you should neglect. One is this one, because charge is attached to this surface, so don't consider this. So charge is attached to this surface also. So 2 surfaces you should neglect, because electric field lines are parallel to the surface, flux becomes 0. Remaining how many surfaces are there? 6 minus 2, 4. So flux through the cube is divided by 4. So that is flux through the cube. Oh, why have I written 4 by epsilon? It is just 4 epsilon. That is equal to q by 4 epsilon naught divided by 4. Flux through the cube is equal to q by 4 for the 16 epsilon naught. Okay. Now one more case is there. What if the charge is placed at any one of the edges? Let me consider a cube here. Okay. Now the charge is placed at this corner, not the edge. Corner. Charge is there at the corner. Charge is at the corner. Now, what is the flux through the cube? Flux through the cube is given by q by 8 epsilon naught, because to the corner of the cube, how many cubes can be connected? 8. One is here, okay, one, this one, 2, 3, and this side 4 to this corner, right? 1, 2, 3, 4, and above 4. So to this corner we can attach 8, what is that, cubes. For edge 4 cubes, for surface 2 cubes, and inside nothing. Now divided by 8. So this one here, through face, if you want to calculate, neglect this surface, neglect this surface, and neglect this surface. 3 surfaces you should not consider for flux through face, because this charge is attached to those 3 surfaces. Remaining 3 surfaces will be there. So flux through each face is equal to flux through the cube divided by 3, that is q by 8 epsilon naught divided by 3, that is flux through the cube, 8 3s are 24, q by 24 epsilon naught. This was asked many a times, it is very, very important. Okay. So this is for the cube. Okay. We have few more, let us discuss about them also, wherein we consider the continuous charge distribution and external electric field also. Sir, what is the flux through hemisphere? Let us consider hemisphere. When you consider external electric field, let us consider there is a electric field entering this, okay, electric field entering here, so at these points and coming out here. What is the electric flux which is entering? Let us consider field, electric field intensity is E. Okay. Now if you observe, flux in you have to write, flux out also you have to write. See, do remember, flux in is taken negative, flux out is taken positive. How much flux is entering? E into area here. So what is the surface area of hemisphere, curved surface area? Don't consider that, because here you have to consider area vector here is outwards, here area vector is opposite to it, area vector is here. You need to consider this component of theta also. If you resolve that electric field with respect to area and all, you will get the same area as that of the bottom surface area. How much is that? Pi r square. The bottom lane surface ಇದೆ ಅದನ್ನೇ ತಗೊಂಬಿಡಿ pi r square, because here you need to consider angle also. ಈ ಕಡೆ angle ಈ ಕಡೆ ಇರುತ್ತೆ, this side angle area is in this direction upwards, here area is in this direction, here is area in this direction. So just take the bottom surface area, that is pi r square. Here same flux will come out. Flux entering is equal to flux leaving, so net flux is 0. Okay, so second case I'll consider. Similarly, there is a cone like this. Okay, cone. The flux entering this in this direction and coming out. So what is the flux in and flux out? If I consider electric field density is E, flux in is taken negative, flux out is taken positive, flux net will be 0 only anyhow. So flux in is E into this surface area, how much? Pi r square, whatever the value that you give. E out also will be same, because whatever the flux is entering which is coming out, sir, here area in this direction, here area in this direction, here area in this direction, area in this direction. So E into pi r square. You understand? So if they give this kind of questions, you should be very careful while answering for competitive exams. Now, sir, what if the flux enters like this? Okay, let me consider. Now, if I consider a hemisphere, flux passes in this direction. Enters here and comes out. Enters here and comes out. So what is the flux now? Okay, what is the flux now? So flux in is negative, given by E into this area. If you observe from sideways, if you observe, this area is half of the circle, yes or no? This is the complete circle, pi r square. So half of it is pi r square by 2. Yes or no? When you observe the hemisphere from the sideways, the area looks like a, this side looks like a circle, half of the circle. Half of the circle is pi r square by 2. So same output will also be there in positive. Flux out is equal to plus E pi r square by 2. Similarly, let us take a cone. This is the hemisphere. Let us take a cone. So the flux enters in this direction. And comes out. So if you observe from sideways, how does it look? It looks like a triangle, right? It looks like a triangle. What is this base? Base will be diameter, half of it is radius. Now, electric flux in is equal to negative, electric flux out is equal to positive, electric flux total, net electric flux is 0. Electric flux in is E into area is the area of the triangle, half into base is radius plus radius, 2 times r, into height, let me consider h, that is minus E r h, output plus E RH flux is 0. Is that clear? Yes or no? So these kind of questions you can expect in competitive examination. Also there is one more question, let me give that. In terms of linear charge density, there is a cube here. Okay, and there is a cube here. There is a cube here. This surface like this, it is attached. Okay. Now there is a wire which is placed along its diagonal. There is a wire which is placed along its diagonal, which is uniformly charged with a linear charge density lambda. Okay, the side of the cube is given by A. Side of the cube is given by A. This side it is A. Now they will ask you to find out the electric flux through the cube. That is given by what? Charge enclosed divided by epsilon naught. But here wire is given. How to calculate the charge? Very simple. Write this formula. Charge enclosed divided by epsilon naught. You have studied that if this is the length of this cube, side is also A. What is the length of the diagonal? Diagonal length of the cube. Diagonal of cube is equal to root 3 into A. Correct now? So diagonal of the cube square is root 2A. Diagonal of the cube is root 3A. So we have studied that linear charge density is given by charge per unit length. Here length is root 3A. Length is diagonal is root 3A. Q is equal to lambda into root 3A. Linear charge density. Substitute this here. So flux through the cube is equal to Q by epsilon naught, that is lambda into length is root 3A divided by epsilon naught. Very simple. You just need to find out the total charge here. Use linear charge density. Linear charge density. So like this, so many examples are there. So yeah, as of now we'll stop it here. We'll discuss about JEE mains and advanced level questions if you, based on this, because it will be very easier in advanced level also to calculate flux. So we'll discuss about that in the coming videos. Till then, take care. Bye bye. So if you feel the content is useful, please share it to your friends and try to support this channel. Thank you so much.